Hi everybody, welcome back to Chem 121. Hope everybody is well rested and refreshed. I am certainly not. I don't know what has been with me, but I have not been able to sleep very much lately. But Maya wants to say hi. Oh, I guess I talked at her and she ran away. We finished chapter 8 yesterday and we moved on to chapter 9. We very briefly introduced the 5 types of reactions in the section that we are going to study. Excuse me, sorry. There are other types of reactions that we will cover in much more detail in the upcoming sections. But for now, using those 5 categories that we talked about yesterday, and the categories were combination, decomposition, single replacement, double replacement, and combustion, apply those to the 4 reactions on the screen. You may have multiple things to apply to a given reaction. Combustion in particular can apply to something, and then it is also whatever else it might be. So go ahead and do that. I'm going to give you about 4 minutes to go over these 4 problems and categorize them. In the meantime, don't forget that quiz number 7 and lab worksheet number 4 are due tonight. The assignments close tomorrow at 11:59. Make sure to get those in before the deadline. Quiz number 8 got posted last night. I have set the deadline for Monday, March 7th, and then it closes 24 hours after that on Tuesday. All right, go ahead and do these problems, and I'll check back in with you in about 3 or 4 minutes. See you in a bit. one more minute. Once you got your answers, go ahead and type them in the chat, and we'll go over them together. All right, let's go over the answers here. So, oh, first I need the tablet, don't I? Yeah, that's kind of important. Just a second. I have cords for this tablet all tangled everywhere, so I'm trying to fix that. There we go. All right, so I gotta select the pen, don't I? So here in this first one, I have one reactant splitting into different products. So this is a decomposition. I'm just going to ignore that my tablet did that. All right. For the second one, I got magnesium by itself, and if I swap its position with hydrogen, I get the new compound, and then hydrogen is by itself. So this must be, since I swapped two things in one compound, this would be a single replacement. Here I am putting two things together, but one of them is oxygen, so that not only is this a combination, it is also a combustion. There we go. Combustion reactions do not necessarily have to produce like explosions or fire or anything like that. They're just reactions with oxygen. And then the second one here, or not the second one, but the last one, the number 2 in mind because it's a double replacement. I'm going to swap these two. HOH is the same as H2O, so don't let that confuse you. So this is a double replacement. And there you go. All right, those are the categories. Let me know if you have any questions on those. For a lot of today's lecture, we're going to be defining other categories. Like, I think the next one we're going to define a redox. Yeah, we're going to talk about redox reactions here. And then in chapter 10, we're going to talk about a different type of reaction called an acid-base reaction. And that's actually the whole focus of chapter 10, which will be like the last week of classes that we do. All right. Redox reactions are very, very prominent in chemistry and biochemistry. So naturally, we're going to spend like 30 seconds talking about them, right? I would love to talk more about these, but the amount of detail that you need to really understand what's going on in a redox reaction could take the entire period. We're going to try and simplify this the best that we can with some basic definitions. But what redox reactions are any reaction where instead of just swapping the elements around, you are also changing the charges on things involved in there. And so electrons get moved between the reactants as we transform them into the products. And there are a lot of ways that we can do this determination. But we don't have enough time in the quarter to go over all of those mechanisms. So what I am going to do is I'm going to give you some very quick and dirty pointers that will let you recognize, oh, that's an oxidation, or oh, that's a reduction. But first, let's actually define these. Okay, so the first term that we want to define are these two right here. So we've got oxidation and then reduction, which are different types of reaction, half reactions, I should say. And then redox is both of those put together. Now, for redox reactions, we're going to look at these as before-after situations. So the reaction arrow is going to be our subdivider that separates out the before, or the stuff on the left, with the after, or the stuff on the right. Now, very important, when we have a redox reaction, we have both an oxidation and a reduction. What do those terms mean? When something is oxidized, that means that that substance lost electrons. What does it mean to lose electrons? That means that its charge becomes more positive. So an example of this would be, if I had calcium metal, and I took away 2 electrons and I made it this would be an oxidation. Now, I can't just delete electrons. You can't just throw them in the bin and have the rubbish man take them out to the curb. You have to give them to something else in the reaction. So the opposite of being oxidized is called being reduced. Reduced means that a substance has gained electrons. And this is probably where you're saying, well, that doesn't make any sense. Why would you say you're reducing it if you're giving it more stuff? Well, where you're reducing is its charge. So down here at the bottom, if I have chlorine and I give it an electron and it becomes chloride, that's a reduction. So to put those two things together, as an example here, if I had calcium plus chlorine as Cl2, and I did a combination reaction to create calcium chloride, we would have to analyze this to see what was oxidized and what was reduced. And again, the way to do this is a before-after situation. So what you do is you look at the charges of everything before and after. Stuff that is in elemental form is always neutral. Remember that atoms are neutral entities. They have the same number of protons and electrons. Whereas something in a compound is not necessarily beholden to that restriction. So if you see calcium metal by itself and you're asked, oh, what's its charge? Well, it's 0. It's an element. If it had a charge, I would have written one, right? But by itself, as an element, it has 0 charge. Same thing right here with chlorine. I cannot do this. They do not both have a minus charge, because if there were 2 of them, then this would be true, right? There's no charge written there. This is elemental chlorine. So its charge must also be 0. But over here in the calcium and the chlorine combine to make calcium chloride, I make an ionic compound. Remember that ionic compounds form from electron transfer. Remember this, where we were like, here's my chlorine. And I'm going to go, whoop. Well, guess what? This is my oxidation and this is my reduction, right? So when I look at the charges on each of these things, I would then do the following analysis. Now I have to erase all this, which is... So I'd say, okay, calcium started as 0 and it became +2. So calcium lost 2 electrons and was therefore oxidized. Chlorine, on the other hand, started at 0 and became -1. So each gained 1 electron and was thus reduced. So if you were given a reaction like this, calcium plus chlorine gas makes calcium chloride, and I asked you which element was oxidized, you would say calcium was oxidized. And if I asked you which one was reduced, you would say chlorine. So this is the gist of redox reactions. Remember that if something is oxidized, something must be reduced. So it's redox, it's both. You can't only have one unless you're writing like a partial reaction like this. So this is not a full reaction. Hey! No, sorry, I had to stop cats just a second. Sorry, I didn't mean to yell in the microphone at my cats. All I heard was meow, meow, meow in the background. They didn't exactly leave each other alone, so I'm going to have to stand up and deal with that again in a second here. Now, how do you remember the convention for which one's oxidation and which one's reduction? So the mnemonic that I use is oil rig, where oil stands for oxidation is losing electrons, and rig is reduction is gaining electrons. Oh my goodness, my cats are still yowling at each other. I'm gonna have to like go throw like a ball at them or something. Or a pillow. So that first reaction that I showed you was one way that we can determine a reaction is oxidized or reduced. So you can look at the charges on the ions. That can get complex very quickly, particularly when we're dealing with organic compounds, such as stuff that has carbon, hydrogen, and oxygen in it. So what we're going to do is we're going to sort of shortcut this and add the following hints, we'll call them. If you add oxygen atoms to a substance, or you just make more bonds to oxygen, what you are doing is oxidizing it. So if something starts off not bonded to oxygen, and then after the reaction is done, it is bonded to oxygen, or there are more bonds to an oxygen within the molecule, the process that substance has undergone is oxidation. This is in fact why we call it oxidation. Oxygen loves electrons. It's very electronegative. It takes electrons from everything, except fluorine, but we don't talk about it. So anything that oxygen gets bonded to, it's going to say, yoink, these are my electrons. And when you form more bonds to an oxygen, you're giving it more electrons to participate in that bond. On the screen, I have two examples of a reaction that are written in what's called organic nomenclature, or organic notation, we'll call it. Nomenclature would be the actual naming. What this notation means, I'm going to just say nomenclature over and over, aren't I? What this notation means is that we draw stuff that looks like this. You might have seen little stick figures and diagrams like this, or maybe they look like this, and they might have like double bonds or stuff like that. And then they look like they have little faces or stuff inside these hexagons. What this notation is saying is that at every corner, we have a carbon. If an atom is not written and it's just a corner, or it is the end of the line, those are all carbon atoms. So how many carbons are in the zigzag I drew? There would be 1, 2, 3, 4, 5, 6 at this junction in the middle, 7, and then 8 at the terminals. So there would be 8 carbons in that above diagram. In this benzene ring here, there would be 6 carbons, 1 for each point on the hexagon. In these drawings over here in my reactions, this right here is a carbon, so is this intersection in the middle. I'm pointing kind of at the bond there. I want to point at this intersection here, and I'll set this one. And then so is this intersection here. So these are all examples of carbons. Any lines coming out of your carbons are bonds, and we still fulfill the octet rule. Now, you might be looking at some of these and going, well, wait a second, all the things at the end points have only one bond coming out of them. That would only be 2 electrons. That wouldn't satisfy the octet rule. Well, that's where the second rule comes in, and that is fill in enough H's for the octet rule. So, for instance, this carbon right here actually also has 3 H's attached to it. They're just not drawn because drawing out all these H's, this one would have 2 because I need 2 more bonds to get to an octet. This one also has 2. Notice how tedious this is for me to draw these out. You're already sick of it, right? There would be 1 H here because I need to have a 4th bond. I need 3 here. Also, look how hideous it is. Oh, it's disgusting. So we don't do this shit. We don't draw in the H's, and we don't put C's at all the junctions. It's all implied. If you take Chem 131, which most nursing students probably should, I don't believe everybody has to, but I think it's a very good class to take. You work exclusively in organic nomenclature, so this is your first little sort of dip in the pool, I guess we'll say. And then you get to do all the cool reactions. Like, the reactions we've done in this class have been very elementary. You get to see some really awesome stuff in OChem and biochem. Alright, so we now know how this works to draw out these structures. Now let's try and interpret the structures over here. So I'm going to clear, not the screen, if I can avoid it. I'm going to clear out these arrows here. How do we determine whether this was an oxidation or not? And the answer is to either add oxygen atoms or make more bonds to oxygen. So here I have 1 oxygen, but afterwards I now have 2 oxygens. So this would be an oxidation, because I got an oxygen in there somehow. And in order to do that, it needs electrons, and it takes them from everything else that's there. Down here, I have 1 oxygen, and I still have 1 oxygen. But initially, it only has 1 bond, and now it has 2. Making extra bonds to my molecule requires us to remove electrons from it. Because oxygen's got plenty of electrons, right? If I suddenly have a deficient molecule, oxygen can kick in those extra electrons and form a double bond. So, if I oxidize the molecule by removing electrons, this happens. Oxygen is forced to make more bonds to other atoms. So, those are the 2 conditions to look for. Look for additional oxygen atoms being added into the structure, or I have 1 oxygen already there, or however many. I just have to make more bonds to it. All right. So these reactions would classify as oxidations. What about reduction? Reduction is doing the opposite of this. One way to get rid of oxygens is to just chuck them and replace them with hydrogens. It says we've added H's, but they're just not there yet. There they are. Now, if there aren't any oxygens in there at all, you can still do reduction by adding H's. So in this reaction here, I've added hydrogen, H2, and I've removed a double bond and turned it into a single bond. The only way that I can do that is by adding electrons to the structure. And those electrons come along with hydrogen, because remember, H has 1 electron. 2 H's would have 2 electrons, so I've added 2 electrons to the structure. If you want to see what the mechanism looks like, you can imagine that this bond right here is these two electrons. Here's a bond between two H's. I'll make the dots real big. And so the new bonds that we would end up making would be these two. So this bond breaks, this bond breaks, this bond forms, and this bond forms. And thus, these extra electrons that were not part of the structure now are. We have added electrons to the structure, and therefore it's a reduction. And yes, this is the easy part. This is probably already super confusing. So that's why we're literally not going any further with this, is because the rabbit hole goes quite deep here. So for your purposes, you should be able to do this first thing that we showed, that I erased, unfortunately, off the screen here, with the basic elements and then figuring out their charges before and after. And then looking at sample reactions and seeing, oh, did we add oxygens or bonds to oxygen, or did we remove them? All right, so I'm going to put the practice problems on the screen here. I'm going to number these 1 through 3. I'll number it over here. And I apologize that these are low resolution because I didn't have Chem draw at the time when I made these slides. What I want you to do is tell me, is the reaction an oxidation or a reduction? Now, this is the overall reaction. We're also doing other things. So, the structure that I care about to answer this question is whatever we're starting with here. So, you might be saying, well, wait a second, isn't it always both? Because you just said that you have to do both. I want it from the perspective of this. The other thing is happening to these guys, which you've probably noticed, hey, they're not written like normal reactions that we've seen. And that's because in organic notation, we don't write balanced equations anymore in organic. We want to know what happens to the structures, and we just assume that the reaction is balanced somehow. You're going to love OCHEM. Because, I mean, there's two schools of thought for organic chemistry. One is, oh, I can just ignore and neglect all that shit that I didn't care about. And then the other is for pedantic people like me, where you're like, well, the equation's not balanced. It doesn't make any sense. Where the fuck does the sodium borohydride go? It's not in my product. I don't understand. And now you'll understand why I came to, initially hate organic chemistry. I love OCHEM now. I think it's so cool. It's like a puzzle. But if that's how you feel about that, you're just looking at that, just ignore this shit. Nobody gives a crap about it, right? Just ignore what's in the middle. That is in the middle just to tell you what is going on at a more advanced level. So tell me if reactions 1 and 2 are oxidation or reduction. And then in reaction 3, I want you to tell me which element was oxidized and which one was reduced. Try and do that. Give you 5 minutes to do it, and I'll check in with you in a sec. would you like to say hi? Hello? 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 That was cat for hello. Let's do one more minute and we'll go over the answers. All right. Do you want to say hi again? Hello? No, she has said hello enough. All right, so for the first reaction, let me clear all of these extra lines out of the way. For the first reaction we've got here, before and after, I had no oxygens on this structure, right? And then after, I have only oxygens, so this was an oxidation. For reaction 2, I have 2 bonds to oxygen. And then I apply something to it, and the result is I only have 1 bond to oxygen. So this was a reduction. And again, that just means, okay, this structure has more electrons than it started with. Oxidation means, oh, it has less electrons than it started with. This is going to be relevant for biochem when you talk about the electron transport chain. And where do the electrons go? They go from here to there to everywhere, sort of thing. All right. Which atom was oxidized and which one was reduced? Well, if I look at iron before and after, where's my cursor? There it is. It's up there. If I look at iron before and after, before it's full of oxygens, and then after it has none. So this iron must have been reduced. Because remember, oxidation would be adding oxygens, reduction is removing them. This carbon, on the other hand, collected all of the oxygens, so the carbon was oxidized. And what is oxygen? It's just part of the reaction. All right, that's redox. That's as much of it as we're going to do. So let me know if you have any questions on that. All right, and this slide just says, hey, what we have done is very basic. It's super basic, but good enough for us. All right, let's talk about how reactions actually occur. So up to this point, we have sort of just said, oh, if I put A and B together, magically they react. You put them in a box and then shake it, and out comes the product, right? Like, it's basically a mystery what happens in the box. So we're going to try and uncover part of that mystery. All right. So the first thing that we need to talk about is the logistics of a reaction. For a reaction to occur, we would create or break bonds. In order for us to do that, I have to have 2 molecules or 2 atoms or whatever bonk into each other appropriately. Now, what is meant by appropriate? I'm not sure if I actually have these slides in the lecture, so I'm going to check real quick. Do I have the picture of the orientation factor? I don't, so we're not really going to worry too much about orientation. But suffice it to say, I guess I could just draw a picture of it real quick. So So we're going to talk about the first property as our focus, but let's talk about the second one really briefly. Let's suppose this is the reaction that everybody uses for a demo. So they say, okay, I'm going to take this, and I'm going to react it with this. All right, so I'm going to do this reaction, and I'm going to react it with chlorine. All right, and so what we're going to do is we're going to move this chlorine around somewhere. Now, if I don't want to cut this, I want to move it. Oh, yeah, there we go, okay. If I were to bonk this chlorine, so this is this chlorine right here, into this molecule to make the reaction, and I bonked it over here, would I make the desired product? Would I make Cl2 and NO? And the answer that should immediately come to your head is, well, no, that would form a bond between Cl and N, right? I don't have NCl as my product, so having this molecule go doink is not really going to solve anything. Likewise, if it bounces over here, I'm not going to form the bond that I want. But if I bonk into it from this direction, then the Cls could pair together. I could break the bond between O and Cl, and I'd form NO, right? That seems plausible. Make a bond, break a bond. And that's actually what happens. So this will only happen, though, if this chlorine bonks into this molecule somewhere over here. Anywhere else on the other side, and we can draw that. Anything over here on this side, I can't draw there because I haven't selected everything. There we go. Any collision over here in this area will not lead to a reaction, so no reaction. But if I bonk into something over in this side, a reaction can occur. So the orientation of the molecule and where collisions occur is important. Now, depending on how complex the reaction is, based on like the molecules that are involved, the orientation may be extremely specific, as in like only 1 in maybe a million collisions react. So the shape and size of molecules becomes extremely important. And we're going to talk about that when we get to enzymes in biochem in 131. Okay, so that's just what that second part about orientation is asking, in case you were curious. I didn't mean to go to the title card. Yep, we're all done. Goodbye. No, I wish. Take a nap, right? All right. The important thing that we're going to study for this section of the lecture is going to be this statement here. Molecules have to move fast enough to attain the minimum amount of energy, otherwise known as the activation energy. Now, I can draw a picture of that one, too. What is activation energy? Activation energy, quite simply, is if I have two atoms that are next to each other, what energy is necessary for the result to be the formation of a bond? And not they just carom off of each other. Careen, I think is the word I was looking for. Now, why do we have to worry about this in the first place? Well, remember that all along the outside of my atoms are valence electrons. And this is true of any atom or molecule I have. I have electrons along the outside. If I were to scooch these close to each other very, very gently, they would immediately repel because there are electrons on the outside, and that's the first force that they come in contact with. Even though there is a different arrangement of electrons that is energetically more stable, if I can get the electrons close enough, I can form a bond, but I have to overcome this initial repulsion first. So the activation energy is the amount of energy is the amount of energy to cause a reaction. If I have reached this minimum amount of energy, I will activate the bonding process. Or I will activate the breaking of a bonding process, depending on what I want the reaction to do. So we're going to concern ourselves with energy for this discussion. Now, because energy is involved, and energy relates to temperature, and temperature is just the speed limit of how fast things go, that means all those concepts are related. So if a reaction releases heat and makes the temperature go up, it must be giving energy to the surroundings. And that means that the substance itself has energy in it in its bonds. And we give that up when we make the new bonds. So what that means is that if we were to describe this as a difference in energy between products and reactants, and I were to, say, draw a y-axis for energy, then what I would say is that something higher up on the scale would be higher in energy, and something lower down would be lower in energy, right? That's just how the y-axis works. I realize this is not the best blue I could have picked, sorry. All right. If my reactants have more energy than the products, then what will end up happening is first I have to overcome the activation energy. So I put a little energy in, and then heat gets released because energy flows out of the system. The reaction loses that energy and gives it to the surroundings, which would be you, for example. If you were holding the reaction or the vessel it was occurring in, and the reaction vessel suddenly became hot, that's because the energy stored in the bonds leaves the molecules and enters your hands. Or your, I don't know, face or arms or wherever you have like this hot pad. I'm envisioning a hot pad, basically. So what we have created here is called an energy diagram. And what the energy diagram does is it plots energy of the reactants and the products against each other. Now, what is the x-axis? This is what's known as the reaction coordinate. And you might look at that and say, well, that looks kind of sloppy, Wes. Why did you do it in a different color? Well, the reason I did this in a different color, and I'm totally making this up on the fly, is because if I had a reaction from A to B, the reaction coordinate is literally this arrow right here. So on the left is the reactants side, and on the right is the products. And in the middle is our transition from reactants to products. So there is an in-between state. And that would be where A is partially on its way and turning into B. Like I'm trying to break a specific bond, and I haven't broken it all the way yet. All right. So what we're going to do is we're going to draw diagrams with the reactants and the products at different energies. And then we're going to draw a little curve to connect the two to show what energy is put in and then what energy is released. All right. So I'm going to clear this because we're going to add a bet. I've drawn these diagrams already on the next few slides here. So we're going to consider this reaction. I'm going to mix A and B together. When they combine, heat is released. So this would be a hot pack reaction. Since the reaction releases heat, that energy had to come from somewhere, and that came from A and B. The product, AB, must have less energy as a result. And so if we draw it on a diagram, it'd look like this. How much energy was lost by the reaction? Well, I started with this much energy, and I ended with this much energy. So the difference between those would be the energy lost by the reaction. You might see this referred to as delta H. The H standing for what we actually call enthalpy in chemistry. But for your purposes, it's delta heat. Just call it delta heat. Where did the heat go? The top part with the little hump up here, let's get a new color. This right here, I started with this much energy on the purple line. I had to provide this much energy to get the reaction to go. Because if I don't provide enough energy, I just end up back where I started. If I do have enough energy, though, I get over the hump and then I end up here. So this energy must be the activation energy. And so that's our diagram. Our diagram will show the activation energy for a reaction, which is the difference between the reactants and the peak of the hump. And we'll also show the energy lost by the reaction, which is the difference between the reactants and the products, operating on the assumption that the reactants have higher energy. Then the energy is lost. In a second, we're going to flip the diagram around, or I'm going to have you draw a flipped diagram, actually. And then I'll have you, like, type it in the chat with, like, ASCII art or something like that. Alright, so this is a reaction where energy is coming out. Remember what happens when energy comes out? When we talked about it for phase changes, this would be a reaction that is exothermic. Because the energy goes out of the reaction. So the opposite would be an endothermic reaction. And what I want you to try and determine is what would a diagram for that look like? We'll do that in a second here. So exothermic reactions release heat. Because you are not the reaction and you are the outside of the reaction, you feel the heat that is released. Exothermic reactions feel hot to your hands. A cold reaction would be an endothermic reaction. The heat is drawn out of you and into the reaction. Now, because heat is required to make the reaction go, we would write it as a reactant. So back here, when I had this equation right here on the board, where I had heat as a product, and it feels hot, you could instead have the heat on the reactant side over there, and the reaction would feel cold, because you are putting the heat into the reaction and using it to make the reaction occur. You don't get the heat back. You are supplying it. So this would be a cold pack, which is where I want you to do this example. I'm going to leave this on the screen for like 1 minute or so here, and then we're going to go take our break. Not really a minute. I'm going to do it for like 20 seconds. So you pause the video if you want to work on this during the break. And now we're going to go to our break timer. And then I'm going to hit this button. And then I'm going to hit this button to get some more music here. Hey, we landed exactly on 10 minutes. Hooray! Alright, let me wind this down here. Alright, what I want you to do is I want you to try and determine what the diagram for a cold pack would look like. We saw a hot pack. So let's suppose that you are mixing two things together, A and B. They're the two chemicals in the hot pack. Or the cold pack, I'm sorry. Once you mix them, you form AB. The resulting reaction feels very cold. So what I want you to do is write a chemical reaction for this process. Add the heat somewhere in your reaction. It should be on either the reactant side or the product side. Label the reaction as exo or endothermic, and then draw the energy diagram. I realized that I read these backwards. I was just saying them off the top of my head how I was thinking about them. You could do these in any order, really. Okay? Go ahead and try this. I'm going to give you like 5 or 6 minutes to do it, and then we'll go over the solution together in just a bit. All right, one more minute to draw your diagram. We'll go over the results there. All right, let's go over here. So let's put this much on the screen for now. And then what we'll do is we'll clear all this. All right, so first let's draw a generic energy diagram. So that would be something like this. On the y-axis would be energy. And then on the x-axis would be reaction coordinate. All right, so if the reaction is cold, here's my reaction. I'm going to just draw it as this little like speck right here. Cold means that energy is going into the reaction, right? So wherever my reaction starts, by the time it's done, it will have more energy, right? So my diagram should look something like this, where here would be A plus B, and here would be AB. Now, if I did this as my diagram, I just kind of went bloop like that, I don't really have an activation energy, do I? In fact, the reverse reaction would just kind of fall right back down, and I would never make the product. I would just fall back to the reactants. You can kind of think of these diagrams as like a hill. You just see, if you drop the ball on a certain spot, where will it roll? And if the answer is, well, it always rolls to one side, you don't really have a reaction there, right? So this line isn't going to be any good. But to have an activation energy, we would go up a little bit over this line, and then we'd come down a little bit. So what this means is that I would need to put in this much energy. Here's my activation energy. And then the heat that is gained by the reaction would be this much. I realize I'm using blue and purple, and that's not very visible for differences, and I apologize there. So here's what your reaction would look like, and then after we have done this, we could write the reaction here. So A plus B. I have to put heat into the reaction to get to do this. So that would be what our diagram looks like. All right. Hopefully that's what you got. If you have any questions, let me know. All right, there's the homework practice at the bottom. All right, we've talked about energy. And we said that energy and speed of a reaction were somewhat related. And they are. But there are other factors that contribute to how fast the reaction itself goes. And we're going to talk about those factors here. Some reactions go extremely fast. Like you snap and the reaction is done. Other reactions are extremely slow. So slow they have... Oops, I've got to click over here. So slow they have... I didn't actually have that line in there. I guess I deleted it. I used to have a line that said slowly with like 30 O's. Because I showed like a picture of erosion of a natural landscape or something like that. We can say how fast a reaction goes by ascribing it a rate. And the study of rate is called kinetics. Kinetics is important because some reactions you want to go fast and others you do not. For instance, if a medication is absorbed by your body too quickly, it can be more dangerous than it was without the medication, right? In fact, that's what a poison is. If you have too much of a certain substance in your body, it is poisonous. Medication, to some extent, is just microdosing poisons, right? So if we can control the speed at which a reaction goes, we can get beneficial effects out of it. And if we want it to do things like be explosive or cause destruction or whatever, we have those options. We have things that we can do because there are certain things we can control to affect the kinetics of the reaction. So we're going to study 4 different things when we talk about kinetics. Those 4 things are going to be the physical nature of our reactants, how much of them we have in our solution or their concentration, how hot the reaction is, and also do we have this special doohickey or MacGuffin called a catalyst. These all affect speed of a reaction in very different ways. We're going to talk about them all here 1 minute at a time. I'm also going to show you a bunch of videos on these. This is the video portion of the lecture. So, all right. For our first example, we're going to look at physical nature. I'm me yawning. Excuse me. I knew that was going to happen at some point. All right. Remember that we said that you have to have enough energy to react with something by colliding into it. But before we even get to the part where you have to have enough activation energy, you have to get to the part where you actually collide in the first place. If you don't have an opportunity for a reaction to occur, it doesn't, right? If A and B can't meet, then A and B won't react, right? We can only do this where the reactants can touch one another. That sounded better in my head. Where the reactants can bonk into... You know what? Never mind. You get the idea. I'm just going to show you the picture. On my screen... Oh, you can see it very clearly on the display over here. I have a solution of B, which is the blue liquid. And then I have A, which is my solid. Which of these should react faster? Well, in theory, if I have more places to react, the faster the reaction should go. But which place or which beaker has more places to react? Well, A and B can only contact each other on the surface because B is aqueous. This is the solution and A is the solid. So what that means is that anywhere on the surface works, but anywhere in the middle will not. So I can't have my liquid react with something in the core of the solid. That it can't reach it. There's no way to get there. So what it comes down to is which of these configurations has the higher surface area. And if I draw colors around here, you can see that this pink line on the outside is reproduced over here. And on top of that, I have this inner darker purple representing additional contact area. So on the surface of A, in the second beaker, we should have a faster reaction because there is more surface area. In fact, the finer ground up your stuff is, the more it will react. There's more opportunities for the liquid to contact the solid. All right, so let's show that in a video here. And the question I'm going to ask you is, which container that you're going to see in this video has the most finely ground calcium carbonate? I'm aware that my browser is up to date, YouTube. You do not need to tell me that. Just open the damn link. Oh, for fuck's sake. I don't know why it's doing this. Hold on. Can I can't even open this hyperlink. Sorry, give me a second. Open hyperlink. Oh, for fuck's sake. I'm literally streaming to YouTube. Why is it not connecting to YouTube? Open the damn hyperlink. Why? Why is this a thing? Edit hyperlink? Sorry, technical difficulties. There we go. For some reason, when I paste the link in there, oops, it will work. Okay, cool. So now I just have to... technical difficulties. Sorry about that. How surface area affects a reaction. There we go. All right. Nobody's using the chat anyway, so I'm just going to cover you guys up. All right. So this reaction involves hydrochloric acid, which is in these beakers right here, and then these bins, or these little bowls that have calcium carbonate in them. So I'm going to add these, not me, this is some other scientist. We're going to add these to the beakers, and your task is going to tell me which beaker, going from left to right, has the calcium carbonate that is most finely ground up. So there's the first one. We've poured it in there, and you can see that the reaction is occurring. It's bubbling and hissing a little bit. Now we'll do the second one. Looks more vigorous or less vigorous. I'm going to leave that up for your interpretation. Then we're going to add the last one. I think it's pretty clear. All right, so in the chat, tell me which reaction do you think had the finest ground powder? Was it left, middle, or right? Oh, directed and produced by Michael West. Can you imagine writing the storyboarding for that? I don't know. Here, we'll just put it right there. Tell me what you think. Which one has the finest ground powder based on what you saw for the rate of the reaction? Far left one is finer ground, and that's not just because you saw it was finer ground when they poured it in, right? Also, thank you for using the chat. I was just about to go check to see if anyone was actually watching. Yes, there are 2 to 3 students watching, so. All right. So that was our video on how fast a reaction can occur based on surface area. All right. Like we said already, for reactions to occur, they have to bonk into each other, right? The molecule A has to meet molecule B. Let's suppose that we had 2 solutions that were both inside a 1-liter beaker. These are different beakers, by the way. So solution 1 in beaker 1 is 1 mole each of A and B, whereas solution 2 is 1 mole of A and 4 moles of B. Which of these would react more quickly? Well, if I draw a little picture like this, you could see that for a given molecule of A, it has 2 options of things it can bonk into. It can bonk into another A, which would not do a reaction, or it could bonk into B, because there's equal amounts of both, right? So, solution 1, 50% of collisions would result in a reaction. Solution 2, on the other hand, A could bonk into another A, or it could bonk into any of these Bs. There's 4 times as many B as there are A, so 80% of the collisions would react there. And since there are more opportunities to react, the reaction goes faster. So the more concentrated something is, the faster the reaction occurs. This one I don't have a video for because I couldn't find an appropriate one. But we have 2 more videos, don't worry. One of them is Jimmy, is it Jimmy Kimmel? I think so. We'll show that in a second. I'll definitely get copyright dinged for that, but that's okay. It's a great video. All right. Now, gases operate by the same rationale. Higher pressure is the same thing as higher concentration. There are more molecules per unit volume at a higher pressure. And so if you increase gas pressure, you can increase the rate of a reaction in the gaseous phase. All right. What about temperature? Remember that temperature is the speed limit at which molecules can go. If the temperature is too cold, you can never have enough energy to get over the activation energy. And so cold reactions tend to go very slowly because a very small fraction of molecules can actually make it. Hot reactions go much, 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 much faster. Those molecules have more energy. They're more likely to have more energy to go over the activation energy. And so we have an example here of glow sticks. Oops, whoops, this is not what I want. This is the opposite of what I want. Goodbye. Let me fix this. I hit escape and I meant to not do that. There we go. Oh, for fuck's sake. Why is this... Stop telling me my browser is up to date. Just open the goddamn link. Sorry. I'm very mad at YouTube now. There, now it worked. I just had to click through it like 17 times. Oh, I hate technology sometimes. Alright. Now there are people chatting, I don't feel obligated to cover it up, so I will reveal you lovelies for everybody to see. Alright. The only real issue I have with this is that the glow stick on the right looks a little dimmer than the one on the left, but the intensity in the center, I'm going to just illustrate where I'm trying to refer to, like right here in the middle, should be approximately the same for the purposes of this reaction. What we're going to do is we're going to dunk the glow sticks. One's going to go into a hot bath, and the other one's going to go into a cold bath. This is what's known as a luminescence reaction. When the reaction occurs, instead of heat being emitted, light is emitted. So the product of this reaction is actually light. Light is a form of energy, just like heat is a form of energy. So we're going to put this in here. If the reaction speeds up, it should get brighter. And if the reaction slows down, it should get more dim. Let's see what happens. Which beaker is which temperature? So in we go in the first one. Hint, condensation means cold. Into the second one. And then, I don't know if they time-lapse this, but I'm going to time-lapse this by just going forward like this. Can you tell what is happening to the reaction? Oh, I guess we're already here. Which beaker was which? Which one was the hot water? Well, clearly the one that's glowing brighter must have gone faster, right? There is more energy available to produce more light as a product. The cold reaction on the right, however, slowed the reaction down significantly. Very limited amounts of light were produced. And as a result, you get a very dim glow stick. Now, this does preserve the reaction. So this is why if you're given like glow sticks or stuff like that, if you want to keep them for longer, which I don't know why you would, but I sure did this as a kid, you throw them in the freezer. They get real dim, but then when they warm back up, they're really bright. And then you can do whatever it is you would do with glow sticks at home. I don't know. You're not at the rave anymore. Just let it go. Oh, well. 11-year-old Wes really liked the glow sticks he got at the fireworks festival for 4th of July, so he kept them in the freezer. So that's why I'm telling you that anecdote there. All right. One more kinetics thing that we're going to talk about. The last one is the catalyst. A catalyst is just a MacGuffin that you add to your solution. Now, the identity of the catalyst is important. Specific reactions require specific catalysts. But a catalyst can be literally anything. It could be like an etch on the wall of your glass beaker so it's irregular. Or it could be copper metal that you have like either finely dispersed as a powder or just like even a flat surface, like you drop a penny into the reaction or whatever. The thing about catalyst is it has to meet these two requirements. It is not used up in the reaction and thus is able to be reused. And it provides an alternative activation energy. So, not being used up is very obvious. Okay, I involve it in the reaction in some way, and then when I'm done with it, I just put it back. That's cool. We can figure that part out. But what do I mean about alternate activation energy? If I were to draw a diagram for an uncatalyzed reaction, it might look like this. And the red line is the activation energy. But with a catalyst, the activation energy is lowered because a different reaction happens. I am no longer combining A and B into AB. I am combining A and B with a catalyst, and then combining that catalytic thing with something else that then produces the catalyst by itself again, which can be reused, and AB. So that first activation energy might be like A plus the catalyst, which pins the molecule in place so that B can react with it much more frequently due to its orientation factor, or something like that. So that's just an example of a catalyzed reaction. So when you add a catalyst, the activation energy is reduced. And as a result of that, more molecules have the energy to overcome the activation energy barrier and thus react. And so the activation energy doesn't inhibit the rate anymore, so it goes faster. We're going to look at the reaction of peroxide here. Hydrogen peroxide is something you may have in your medicine cabinet in the bathroom. Hydrogen peroxide is stored in a brown or opaque bottle because light causes it to decompose. It turns into water and oxygen, which aren't dangerous. It's not what you paid for, right? You paid for hydrogen peroxide. You want to keep it that way so that when you need it for like cleaning a wound or gargling or whatever, you have it available, and it actually is that rather than just oxygenated water. Now, this decomposition will happen over time, but it is very, very slow. What we can do is add a potassium iodide, well, it's potassium iodide in some cases. Sodium iodide will also work. If you add sodium iodide in the presence of iodide, that's the important thing. The peroxide will decompose into hydrogen and oxygen very rapidly. And this is a reaction that we call elephant toothpaste. Yes, I know my browser's up to date, YouTube. Oh my god, I hate it. I hate it so much, you guys. Oh, why is this a thing that's happening? I don't understand. I keep getting this pop-up that says your browser is up to date. You can use YouTube's latest features. And I don't want that. I want it to show the video I'm trying to link. Oh my god, I hate it so much. Alright, hold on. Who knew that I was going to show you YouTube videos today and instead just be filled with rage and anger? Alright, we'll paste this video into the chat here. And it worked. Of course it works. I don't know why it didn't work the first time. Okay. Alright. This is definitely going to get me dinged, so I hope you guys enjoy it. And I'm actually going to turn on the audio for this. Here we go.
Okay, great. All right. So, all right, so what do we do?
We're going to get started. We're going to start with a little bit of, actually, dish soap. So if you want to put some dish soap in your flask.
How much? Just a squirt?
Yeah, a little more. That's good.
Okay.
So dish soap will keep the bubbles, because we're going to remove the oxygen. They'll hold the oxygen.
Okay.
Okay, so I'm going to just explain what's going on here. So if we go back to this reaction here, the reaction is peroxide decomposes into water and oxygen. The dish soap that they added in here is added so that the oxygen gets trapped in the bubbles and then makes something fun and visible. Because if it's just releasing a gas really quickly, it's not super visible. But if you add a surfactant or a detergent that is very viscous, the oxygen gets trapped in it and you make tons and tons of bubbles. And everybody loves bubbles. That's fun. So that's what we're doing. Also, I'd like to comment that every time a liquid is added to a container, a song plays. And I kind of wish that this was a thing that existed in real life.
So I'll put a little bit in here. All right. Next, coloring. We have green and red. Do you have a preference?
I'll take red.
All right.
It's be very Christmassy. How much of this?
And just keep going. Keep adding a lot of that.
Okay.
That's good. A little more.
This is going to be delicious.
All right.
Is this how you did your jacket?
That's good there.
Okay.
All right, so I'm going to add the hydrogen peroxide because you don't want to do that.
Okay. Oh, it's dangerous,
This
right?
is
Okay.
and actually, yeah, let's get all geared up here.
Okay. Good. Put these on my eyes.
There we go. All right, so in goes that. And
Now, what's happening here? What process are we about to see?
So here's what we're going to see. We're going to, in order to remove the oxygen, we're going to use a catalyst.
Okay.
The catalyst will speed up the reaction. So we're going to, that's what's in here. It's a sodium solution. We're going to pour that in, and that's going to remove the oxygen. The soap is going to hold it,
And we're going to smother to death, all of us.
We'll be okay, but it will create a lot of bubbles really fast.
Okay, great.
And usually this is done in graduated cylinders, but we're going to make it a little more intense with these ridiculously large flasks.
Okay, good.
All right. So this is what you...
All right, so before we actually do the reaction here, the reaction is actually occurring. However, for all of the oxygen to decompose out of this, it'd take months to years. That's too slow. We're going to make it do this in less than 10 seconds, okay? Enjoy.
You're going to use, we're going to pour that in there, the oxygen will be released, and we'll watch the reaction. We're going to need to step back after we pour it.
Okay.
All right, here we
Step
go.
back.
Ready, in 3, 2, 1, pour. There we go.
Whoa! Whoa! Wow, that's great. It's like Ghostbusters. Wow. Whoa! That's something.
They never got that camera or light back, I guess. So, that's the elephant toothpaste reaction. And I would be doing that this spring for 5th graders at Everett Community College if we were in person. So if you're still on campus next year, like you're in the nursing program or whatever, look for me in spring. I'll be wandering around during the science fair. And we do this reaction, and all the 5th graders love it. All right. So we saw from the Jimmy Kimmel reaction with Science Bob. The very nerdy guy is Science Bob. He does all these sorts of like demos and stuff. And elephant toothpaste is one of his big ones. I believe he is currently the world record holder for the largest elephant toothpaste, which I believe involves a swimming pool. They poured all this into a swimming pool, and then of course it filled the swimming pool instantly. I want to say that they did this for like a child's birthday party as well, and it was just there's a bunch of stories about this online. You can look it up. It's super cool. All right, so let's summarize. Oops, I'm clicking on the wrong thing here. Let's summarize the 4 things that affect reaction rate. If I want to make something go faster, I can grind it up into a finer powder to have a higher surface area. More surface area means faster reaction. I could increase the concentration to increase the speed of the reaction. I could heat the reaction up, which means that the molecules move faster, they collide with more energy and can overcome the activation energy barrier. And I can add a catalyst, which changes the activation energy and creates an alternate pathway that is easier for reactants to turn into products. Maya, please, why are you like this? She's just sitting here meowing at me. All right. Now, sometimes you don't want a reaction to go fast. For example, let's suppose that you have milk. You bought milk from the store. Why do you think we store milk in a sealed container? Well, duh, we don't want the reaction to go fast, right? The reaction being the spoilage of milk. Okay. Well, consider what a milk container looks like and give 2 reasons why we store milk in sealed containers in the refrigerator. Okay. And then for question 2 here, I have a scientist has a powdered chemical that reacts with water and it makes the solution turn dark blue. But she notices that her prototype only reacts for 10 minutes. And she would like it to work for both longer and shorter durations of time. What could the scientist do to make the reaction last longer And what could the scientist do if she wanted it to speed up and go to completion more quickly? All right. So answer those two questions. We'll go over the results in just a bit, and then I guess we're done because we only have 10 more minutes, right? We'll talk about. We are going to have a class period tomorrow because I do want to finish this chapter, and tomorrow's lecture will be enough to do that. So let's do these questions now, and then we'll go over the results in just a bit. Hello. 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 Maya. Maya. Hello. one more minute, we'll go over the answers here. Maya. 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 Maya, say hi. Hello. No, she doesn't want to say hi. She's been sitting here for the entire time, just like rubbing her head against the armrest. Like, why aren't you petting me? Why are you not petting me right now? All right, so for the first problem here, let's draw a picture of a milk jug and see if that gives us any information. So we've got the lid, and then it looks kind of like this. And then we got the handle. So something like that, right? And when you have the milk in the container, it goes all the way up to about, what color should our milk be? Probably not purple. Let's not do purple milk. Let's just do kind of, we'll do gray just because the surface could look gray. That's okay. Now, this right here, that I'm going to paint kind of like faint purple right here. This is the headspace. The headspace is where oxygen can react with the milk. And that's going to be at the surface. So the first reason, by virtue of us sealing it in a container that's nearly filled, is by putting the milk in this condition, we minimize the surface area for oxygen to react with milk, which would cause it to spoil it. And then the second condition is, well, if it's in the fridge, then it's going to go the reaction between the oxygen and the milk is going to be very, very slow relative to whether or what it would be at room temperature. So there's two reasons that I thought of. You may think of other reasons, but those are the two that I thought. All right. For the second question, we have a reaction where stuff happens in 10 minutes. Now, if the scientist wants to make the reaction go longer, how would you slow the reaction down and make it go for a longer time? Well, what are the 4 things that make a reaction go fast? So faster rate would be to increase surface area by grinding it up. Step 2 would be to concentrate it. So concentrate the reactants. Step 3 would be heat or increase the temperature, and then step 4 would be to use a catalyst. Now, what if you wanted a slower rate? Do the opposite of these. So use a chunkier solid. We could dilute the reaction. That would make it go slower. We could use cold temps. And should we use a catalyst? No. So there you go. If we wanted to go faster, we can use all the things we discussed. If I want the reaction to go slower, we just do the opposite of those things. All right, that's kinetics, and that's all we have time for today. So when we come back tomorrow, because we are going to have a Wednesday lecture, I do need that time available to do this. There's the homework practice, by the way. We're going to finish the next section, the next 2 sections or so. So that's equilibrium and Le Chatelier. How many slides is that? Because if I have time, I'd also like to do a little bit of chapter 10. Yeah, so we'll probably do the equilibrium for the first part. Le Chatelier doesn't take that long. And then we'll do a little bit of acid base. So yeah, we're going to do the rest of chapter 9. We'll start chapter 10, and then next week we're going to do the rest of chapter 10, and that's it. We're done. That's the end of the quarter. There are no more lectures. We made it, right? So we're very close to the end here. I just need one extra day to like fit in the rest of the chapter 9 topics. So that's what we'll do. So I'll see everybody here tomorrow if you can make it. Otherwise, it's just another video you get to watch. Hooray! Question mark, I guess. But I do want to thank the people who were here today for coming out. I hope you enjoyed the videos and the cat and me getting angry at really stupid YouTube shit because computers only cause frustration, I guess. I don't know. Make sure to get the lab number 4 and quiz number 7 in tonight. They close tomorrow. Quiz number 8 is due next week. Quiz number 9 will also be due next week. We'll talk about quiz number 10 next week. It's all next week. See you tomorrow.